Right now, in a region of space 1 million miles from Earth, a telescope is staring backward through time, and in almost every single direction it looks, it keeps finding the same thing. Small, red, impossibly bright, impossibly old, scattered across the deepest images ever taken of the universe like something was left behind on purpose. Astronomers gave them a name that sounds almost harmless. Little red dots. But the more they studied them, the less harmless they became. Because these objects should not exist. Not in the numbers we are finding them, not this early, not this bright, and not doing what the latest evidence now says they are doing. Scientists on this research have used the phrase broke cosmology to describe what happened when they first counted how many of these things were out there. Not bent it, not challenged it, broke it. And in 2026, after 4 years of confusion, after dozens of competing papers, after some of the best astrophysicists alive arguing with each other in real time in front of the public, we finally have an answer for what they are. And the answer is worse than the mystery. Stay with me, because by the end of this, you're going to look at every deep space image differently. I am your name, and this is your channel. Subscribe now, because we are about to go somewhere most science channels won't take you. Before we get to what they are, I want you to actually picture what astronomers were looking at when this started. Not a single strange photo, not one anomaly buried in a data set somewhere. Nearly every deep field image Webb captured, images built by pointing the telescope at one tiny patch of sky and leaving the shutter open for hours, sometimes days, to gather every last photon of ancient light, kept producing the same faint red intruder somewhere in the frame. Astronomers are used to finding rare things. A single strange galaxy, a single unexpected supernova. What they were not prepared for was a population. A pattern that repeated itself across field after field, survey after survey, as if the early universe had scattered the same warning sign across the entire sky and was simply waiting for an instrument sharp enough to notice. Let's start with the machine that found them, because it matters. The James Webb Space Telescope launched on Christmas Day, 2021, and settled into an orbit around a gravitational parking spot called the second Lagrange point, roughly 1 million miles from Earth, on the side of our planet permanently facing away from the Sun. It is not an orbit around Earth. It is an orbit around the Sun, moving in lockstep with our planet, shielded behind a tennis court-sized sun shield that keeps its mirrors cold enough to detect the faintest infrared light in the universe. That capability is the entire point. Infrared light lets Webb see through the dust that blocks visible light, and it lets Webb catch light that has been stretched, redshifted, by the expansion of the universe itself over more than 13 billion years of travel. In simple terms, when Webb looks far enough away, it is not just looking at a distant place. It is looking at an early time. It is looking at the universe as it looked when it was a few 100 million years old, a fraction of its current age, closer to the Big Bang than to us. To build one of these deep field images, Webb doesn't just snap a picture the way a phone camera does. It points at one narrow patch of sky, sometimes no wider than a grain of sand held at arm's length. And it holds that position for hours at a time, sometimes across multiple orbits, slowly collecting individual photons of light that have been traveling toward us since before Earth's own sun had finished forming. Every one of those images is, in a very real sense, a fossil. Not a picture of what exists now, but a picture of light frozen at the exact moment it left its source billions of years ago, only now finally arriving at a mirror built specifically to catch it. When astronomers say Webb is looking back in time, they are not using a figure of speech. They are describing the literal physics of how a telescope this sensitive works. And almost as soon as Webb turned its mirrors toward that ancient light, in the summer of 2022, astronomers started noticing something strange showing up again and again in the data. Small, compact points of light, tinted deep red, scattered through nearly every deep field image Webb took of the early universe. By 2023, researchers had written multiple papers trying to describe them, and they kept finding the same three things in common. These objects were extremely compact, barely resolved even by Webb's sharp optics. Their light, when broken apart into a spectrum, formed a distinctive V-shape, faint in the middle and rising sharply at both ends, and they showed clear signs of high-velocity hydrogen gas moving at speeds that only made sense if something enormously powerful was driving it. Within a couple of years, astronomers had cataloged well over 300 of these things, and that number is where the real trouble started. What made the early discussions so tense inside the astronomy community was that nobody could agree on the most basic question first. Were these small, unusually compact galaxies, packed with young, densely clustered stars, burning bright enough to explain the light? Were they something being deliberately reddened by thick clouds of cosmic dust, sitting in front of an otherwise ordinary object? An illusion of color, rather than a true signature of something new? Or were they something that had never been cataloged before at all? Every one of those explanations had a problem. Galaxies that compact and that bright, This early strained the physics of star formation past its known limits. Dust could explain the reddening, but it struggled to explain the specific V-shaped spectrum and the high-velocity gas showing up again and again. For nearly 2 years, papers went back and forth, one group proposing an explanation, another group publishing data that seemed to rule it out. It was, by the standards of modern astrophysics, an unusually public and unusually heated argument, playing out in real time across preprint servers and conference talks, while the objects themselves just kept showing up in every new dataset Webb produced. Here is why the count mattered so much. Before Webb launched, the leading models of the early universe predicted that galaxies large enough and bright enough to be visible at that distance should be rare in the first several hundred million years after the Big Bang. Structure takes time to build. Gravity needs time to pull matter together into galaxies, and galaxies need time to grow massive enough to produce light we could detect across billions of light years. The little red dots broke that timeline immediately. There were too many of them, appearing too early, glowing with too much light for their apparent size. Some astronomers, only half joking, started calling this problem impossible early galaxies, because if these objects really were galaxies in the traditional sense, entire textbooks on how the universe assembles itself would need to be rewritten from page 1. So scientists went looking for an alternative explanation, and that is when the real theory started taking shape, and once you hear it, you will understand why some people in this field have started using words they don't normally use in peer-reviewed science. Words like terrifying, words like monstrous. The leading explanation now, backed by some of the most detailed spectroscopic evidence Webb has ever produced, is that little red dots are not galaxies at all. They are something scientists have started calling black hole stars. Picture a supermassive black hole not sitting quietly at the center of a fully formed galaxy, the way the one in the middle of the Milky Way does, but newly formed, ravenous, and wrapped in a dense, swollen cocoon of hot, partially ionized gas. As that black hole tears into the surrounding material and pulls it inward, the gas doesn't just vanish quietly into the black hole. It heats up to extreme temperatures under the crushing pressure and gravity, and that heat radiates outward through the cocoon surrounding it. That radiating cocoon is what Webb is actually photographing. Not a galaxy, not stars. A feeding chamber built around an object that, from the inside out, is devouring everything it touches. Try to picture the scale of what that actually looks like up close, if there were anything close enough left to look. A black hole, invisible by definition, sitting at the exact center, surrounded by gas so dense that light itself struggles to escape it cleanly, the whole structure glowing, not because it is producing light the way a star does, but because it is being forced to shed enormous amounts of gravitational energy as heat and radiation. The byproduct of matter being torn apart and pulled inward faster than the cocoon around it can stay stable. It is less like watching a star and more like watching an open wound in the fabric of a very young universe, one that has not yet learned how to heal itself into anything calmer. A team led by researchers studying an object designated Glimpse 177M5, one of the most gravitationally lensed and therefore most closely studied little red dots ever found, published in 2026 what is being called the deepest spectrum ever taken of a single one of these objects. What they found inside that spectrum has been nicknamed, only half poetically, an iron forest. Row after row of spectral lines from iron atoms, the kind of signature you would expect from gas being blasted by the extreme. High-energy radiation of a black hole in a violent, active feeding phase. More than 40 independent spectral lines were found, and every single one of them lined up with what the black hole star model predicted. Not one or two suggestive details. 40 separate pieces of evidence pointing at the same conclusion. But here is where it gets stranger, because a study published earlier in 2026, led by researcher Vadim Rusakov and colleagues, added a detail that flips part of the story on its head. When scientists first tried to estimate the mass of the black holes powering these little red dots, using the same techniques that work for normal galaxies, they were getting numbers that seemed impossibly large for how early these objects appeared in cosmic history. Numbers that, if accurate, would have made the impossible early galaxy problem even worse, because it is even harder to grow an enormous black hole quickly than it is to grow an enormous galaxy quickly. What Rusakov's team discovered was that the dense gas cocoon surrounding these black holes was distorting the light passing through it, artificially broadening the spectral lines scientists used to measure mass in a way that made a smaller black hole look far heavier than it actually was. Once that distortion was accounted for, the true masses came out roughly 100 times smaller than earlier estimates. That sounds like it should be reassuring. It is not, because what it actually means is that these are not slow, steadily growing black holes patiently building mass over hundreds of millions of years, the way our models assumed was necessary. These are comparatively small black holes growing at an absolutely furious, almost reckless pace, consuming matter far faster than anything we thought was physically stable, and doing it in huge numbers, scattered across the early universe in the first few 100 million years after everything began. Think about what that actually describes. Not one extreme object, not a rare cosmic freak accident. A phase, an entire era in the early universe where hundreds, likely thousands of these gas-shrouded black holes were simultaneously tearing through material at a rate that violates what astrophysicists spent decades assuming was even possible, all glowing in the same distinctive red light, all hidden from every telescope built before, because nothing before Webb had the sensitivity in exactly the right wavelength of infrared light to catch them. And then, just as suddenly as they appear in the early universe, they vanish. Little red dots show up in enormous numbers around 600 million years after the Big Bang. And by the time the universe reaches roughly 2 billion years old, they are essentially gone. No clear population of them left. This disappearance is not a minor footnote in the research. It is one of the central open questions driving the entire field right now. And there are only a small number of possible explanations, none of them simple. One possibility is that these black hole stars burn out. Their feeding frenzy is so extreme, so unstable, that it cannot sustain itself, and after a relatively short, violent phase, the process shuts down, the gas cocoon disperses, and whatever is left behind fades, from view in the specific way that made them detectable in the first place. Another possibility, this is the one that gained serious traction in 2026, is that they don't die at all. They transform. In August of 2026, a team led by researcher Pierluigi Rinaldi published findings centered on an object nicknamed the Saguaro, a spiral galaxy close enough to us, in cosmic terms, for its structure to be studied in unusually fine detail. Buried at the center of that spiral galaxy, the team found something behaving exactly like a little red dot, compact, intensely bright. Matching the same spectral signatures researchers had spent years cataloging in the distant early universe, the implication is significant. It suggests that little red dots are not a separate category of object that simply disappears. They may be an early violent temporary stage that some active black holes pass through on their way to becoming the quieter, settled supermassive black holes that sit at the centers of ordinary galaxies today. The same kind of black hole sitting at the center of our own galaxy right now, mostly dormant, occasionally flaring, but nothing like the raw, unstable feeding frenzy captured in these early images. If that interpretation holds up, then somewhere out there, hidden inside galaxies we already know about, there could be the quiet, grown-up descendants of exactly the kind of monstrous, gas-wrapped black hole stars Webb has been photographing at the edge of time. The violence didn't disappear, it just got wrapped in a much calmer disguise. Sit with that for a second, because it reaches further than one distant spiral galaxy. If the Saguaro really is showing us what a little red dot grows into once the feeding frenzy calms down, then the same basic history could apply to the supermassive black hole sitting at the very center of our own galaxy right now, the one astronomers call Sagittarius a star. Today, it is quiet, mostly dormant, occasionally flickering with a small flare, nothing close to the raw, gas-shrouded violence captured in these early images. But if every supermassive black hole has to pass through some version of this stage to reach the size it eventually settles into, then billions of years ago in the earliest chapters of our own galaxy's history, something sitting in that exact same spot may have looked disturbingly similar to the objects Webb is photographing at the edge of the observable universe right now. The monster didn't necessarily belong only to some other galaxy far away and long ago. It may be sitting at the center of ours too, simply finished with its most violent phase long before humans, or anything resembling us, existed to look up and notice. That urgency is precisely why the team dedicated so many months of careful, difficult work to a single computer chip malfunction, rather than simply accepting the loss and moving on. Every additional year, Voyager 1 continues operating adds genuinely irreplaceable data to humanity's understanding of the environment immediately surrounding our solar system, and NASA's engineers clearly understood exactly how much was at stake in successfully completing this repair. It's also worth understanding that this wasn't actually the first time Voyager 1 had produced a genuine mission-threatening surprise in recent years, though the 2023 incident stands out as the most severe. In May 2022, the spacecraft's attitude articulation and control system, responsible for keeping Voyager 1's antenna precisely aimed back toward Earth, began transmitting telemetry data that simply didn't correspond to any physically possible state the spacecraft could actually be in, even though Voyager 1's antenna remained correctly pointed the entire time. Engineers eventually traced that separate issue to the system, somehow routing its data through a different, long inactive onboard computer that had stopped functioning years, possibly decades earlier, corrupting the readings before they were ever transmitted. that earlier episode resolved. After several months of investigation, offered the current mission team a kind of dress rehearsal for the far more serious data corruption crisis that would follow roughly 18 months later, though nothing about that earlier fix fully prepared engineers for the scale of the 2023 problem, since the underlying cause and required solution turned out to be entirely different. Consider, too, just how limited the remaining window for discoveries like this genuinely is, and how that reality shaped every decision the engineering team made during those difficult months, turning what might otherwise have been treated as a routine, unhurried. Repair into something approached with genuine, quiet urgency at every stage. Voyager 1's power source, a radioisotope thermoelectric generator fueled by a steadily decaying block of plutonium, loses a small, measurable amount of usable energy every single year, a decline that has already forced NASA to permanently shut down several of the spacecraft's remaining instruments over the past decade, simply to preserve enough power to keep the most essential systems, including the very flight data subsystem at the center of this entire crisis, functioning for as long as physically possible. Current projections from the mission team suggest Voyager 1's remaining instruments will likely lose the power necessary to continue any meaningful scientific operation sometime before the end of this decade, meaning every month spent troubleshooting a malfunction represents a genuinely significant fraction of whatever operational time the spacecraft actually has left. There's a broader lesson embedded in this entire 7-month saga that extends well beyond Voyager 1 itself, one worth sitting with for a moment. It's a genuine testament to both remarkably durable 1970s-era engineering and to the patient, careful, almost archaeological skill of a modern engineering team willing to spend months solving a single problem most other missions would have simply written off as an unfixable terminal failure. Suzanne Dodd has described the day-to-day reality of managing Voyager as an ongoing negotiation with an aging, increasingly fragile spacecraft, one where every decision has to account for outdated systems, thinning power margins, and hardware never designed to still be functioning this deep into the 21st century. The successful recovery from this specific crisis stands as clear proof that this negotiation, however difficult, can still be won, at least for now, buying Voyager 1 additional time to keep sending home data from a region of space no other human instrument currently occupies. So when you hear that Voyager 1 just sent back something NASA wasn't ready for, understand exactly what that actually means, because the true version of this story is more human, more genuinely tense, and ultimately more triumphant than a single mysterious signal could ever fully capture on its own. For nearly 5 months, humanity's most distant functioning spacecraft spoke only in meaningless, repeating nonsense, the result of a single corrupted computer chip nobody could physically touch, replace, or even fully explain, a genuinely humbling reminder of exactly how far this remarkable machine now sits beyond the reach of ordinary repair. And through months of painstaking remote detective work, performed across a communication gap wider than any repair team in history had ever previously worked. Across, NASA's engineers didn't just diagnose the problem. They rebuilt Voyager 1's ability to speak piece by piece, one carefully relocated fragment of decades-old code at a time, restoring humanity's connection to the edge of interstellar space, and buying this remarkable aging machine more precious time to keep telling us what it finds out there. For however many years, it still has left to send that story home. If a machine built in 1977 can still surprise and ultimately outsmart the very engineers responsible for keeping it alive, imagine what else this incredible spacecraft still has left to teach us before it finally goes quiet for good, carrying its story outward into the same interstellar dark it has spent nearly 5 decades learning to describe. Subscribe now so you never miss the next real story from the edge of the universe.